Good afternoon. We're happy to start the second part of the afternoon with Raoul Penaguiao, who will talk about the tropical critical points of an affine Matroid. Thank you, Raoul.
Thank you, and thank you very much for the organizer for putting together this great conference. So yeah, I'm going to tell you about tropical linear spaces and their critical points. This is joint work with Federico and Chris, and let's get into it. So I'll start by telling you two seemingly unrelated problems. The first one is a bit more on the statistics world. So I know this is not the right crowd for this, but I think it's very useful to keep in mind some of the applications of the tools that we have here. And we start with some vector. This is a generic vector. This will not work for all the vectors, but many of integers. And this gives us a monomial function. And things that people in applied mathematics tend to like to do is we're given a model of an algebraic variety X. And we want to optimize this monomial function on this variety. So this seems to be a tricky problem. Of course, we can find critical points. And this is an example of a variety. And the number of critical points of this function actually does not depend on W, on the vector that we start with, if it's generic enough. It's a property of the variety, and it's normally called the maximum likelihood degree. OK, so now to tie in back to combinatorics, if X, our model, turns out to be a linear space, this ML degree has been observed to be the beta invariant of the matroid associated to the vector space. We've seen matroids in these talks yesterday and today. To any vector space, we can associate a matroid, and to any matroid, we can associate this beta invariant. OK, so this is the first problem. The second problem is on graphs. So what you see now are three graphs, beautiful graphs. One that is our G has a special edge Z. We will contract this edge, resulting in a graph with one fewer vertex and one fewer edge. And then we'll take the dual. So for each region of the plane corresponds a vertex, and we draw an edge between two neighbor regions. So this will be the dual graph. And this is a construction that we can do for many graphs. Of course, if we don't have a planar graph, we cannot do it. But when we can do it, we can play a funny game. We start again with some vector W. This will be our starting point. And we want to find sets of weights. Weights on the edges on the left side, and weights on the edges on the right side. OK? And we will require two things, the compatibility conditions. The first is that they sum to the vector W. So remember, the vector W has, it's not patterned here, but each entry of the W is associated to an edge of the graph G. And the second condition, which is the more combinatorial one, is that whenever you see a cycle, either on the graph G or in its contracted dual version, so if it's in the graph G, that means that the weights of the edges that form this cycle, they attain a minimum twice. There's no unique minimum. And the same thing for the Y vector on the right side, on the right graph. OK, very much combinatorial. We want to find pairs on compatible vertices, weights. Is it possible? Can we construct such all the solutions? How many are there? Yes, this is the motivating problem for telling you about Bergman fans. Oh yeah, first I want to run through an example. So let's try to be naive. Being naive is always a good starting point. So let's put weight zeros in everything on the left-hand side. And this already forces our hand on the weights on Y because of the first condition. Remember, the first condition is the sum of the weights has to add up to this random vector W that I picked. This one, 0, 1, 1, 2, 2, etc. So this has to be our corresponding Y. But we already have a problem here. We see a cycle, A, B, C, D, and the minimum there is unique. We don't like that. So this does not satisfy the compatibility condition. If we're a bit more smart with it, and there's an algorithm, that's what I'm going to present to you, we can pick these zeros and the remaining entries in some sort of magical way, and it turns out that the corresponding y, remember this is forced for the sum condition, satisfies all the cycle properties. Okay, so this is the problem that I'll present to you, how to solve this. And for some reason, it's related to both Bergman fans, tropical geometry, and maximum likelihood. Okay, so this is the overview. I already told you in the introduction. I'm going to tell you what are the matroids associated to some graph. I want to really get into some of the details on graphical matroids. And then I'll tell you what the Bergman fan, what role does the Bergman fan play here. And then we will see that counting these solutions will actually turn out to be computing degrees of varieties. Okay. Everyone cool with it? Let's go. So let's start with my favorite matroids, graphical matroids. They are very simple. I will not define what a matroid is. I'm sure there's people that don't know what a matroid is in this crowd. That's fine. The definition is technical and complicated. I will tell you how to construct a matroid from a graph. So there will be some things called independent sets. And in this case, there will be the set of edges that form forests that have no circuits there. There is something called bases of our matroid, which in this case are maximal spanning forests in each graph. In this case, any spanning forest will have 4 edges. Yes, 4 edges. There's something called circuits. And in this case, the circuits will be the simple cycles of our graph. For instance, ABH will form a circuit. You can define a matroid using circuits, and in this case, those are actually the cycles. So it's a good naming convention. I also want to tell you about the rank of certain sets. You can also define a matroid by defining the rank of each set. These are all equivalent ways of defining a matroid. And in the case of graphical matroids, the rank is the size of the largest spanning forest of your edge set. So in the case of the set A, B, C, Z, that's 4 edges, but the largest spanning forest has only 3 edges, so the rank of this set is 3. Okay? So this is a rank function, assigns a number to each set. So far, simple enough. What can we do with this? We can define flats. Now, flat of a matroid will be the maximal set with a given rank. Okay, this is what you see written there. Let's see now example. These are all flats on our, in this case, graph, but in general, matroid. Any matching, any disjoint set of edges, disjoint in the vertex set, will form a flat. Because if you increase, if you add an edge to this set, you're increasing the resulting maximal spanning tree. Any triangle, so complete subgraphs, will also form flats. And in general, whenever you have a matroid, and specifically on the graph, the set of flats will form a poset, which is a subposet of the Boolean set, which in fact is a lattice. And you can also describe the matroid fully by just telling you the flats. The last notion, the last name that I want to imprint on your mind is the name of flag of flats. It's kind of a funny name, but comes from vector spaces. Flag of flats is just a sequence of flats, one containing the other. You can see here a complete flag of flats because you cannot squeeze in any other flat in between. All flags of flats, all maximal flags of flats have the same length. In this case, will be the rank +1, depending on how you want to count it. And that's it. Okay, so that was flats in the context of graphical matroid. Now, my second favorite collection of matroids are the uniform matroids. We'll actually use this example to compute degrees of Bergman fans. I will just tell you what are the bases of this uniform matroid. As I told you before, this is enough to describe the matroid. In this case, the bases are all sets of a fixed size. With this information, we can infer the rank function and what a flat is. In this case, any set of size k minus 1 will be a flat. Why? Because if you increase the size of this set, you are increasing the rank. Okay, simple exercise. What are complete flags of flats? in this uniform matroid, they will always look like this. So this is an exercise for the audience. Perfect. So at this point, if you understand all the complete flags of flats, you understand everything that I want you to understand in this talk, which is the Bergman fan. There you go. Perfect timing. Bergman fan is a tropical space. Now, I can recognize this does not mean a lot to many of you. So I plopped in the definition, which is some weird requirement on minimum of cycles attained twice. So this is why I have a picture, because I don't like just presenting definitions. And what I want you to remember is that the Bergman fan is going to be a fan. Perfect. It's in the name, so it's hard to forget that. And a point is in the fan if for any cycle, I'm now going to mull over this condition, if for every cycle you look at the weights corresponding to, of the vector corresponding to this cycle, and the minimum is attained twice in these weights. Kind of reminiscent from this problem that we saw in the first few slides of the talk, and it's perfect because this fan will allow us to model this, this problem. That's exactly the intention. I also have here the uniform matroid of rank 2 of size 3. It will have 3 cones. Remember, a fan is a collection of cones. In this case, it has 3 cones. It will always be a collection of cones, and that's also an exercise for the crowd. If you remember, we know all the complete flags of flats, so we know everything about the uniform matroid. In this case, we also know everything about the Bergman fan. Now, this definition here tells you, for anyone that is very well acquainted with tropical geometry, this is very simple stuff, but if you want to actually do combinatorics, it's not very useful. And this is why we are interested in another description, the description of the cones themselves. And I want to present to you this picture. So those are 2 elements that are on the Bergman fan of our graphical matroid. Maybe it's not clear at the moment, but let's check the condition. We know the cycles. There's, for instance, I hope this pointer is strong enough. For instance, this triangle, this is a cycle, and the minimum is attained twice. It's the 1 on those 2 edges. And the way we attain this minimum is we cut the vertices into 2 sections, and all the edges that straddle this cut will have the same weight, the small weight. In this case, the small weight is 1. The other example here, the cut will leave this vertex isolated. And then we iterate. This is a very simple way of finding points on the Bergman fan, but now the most important question is, are we actually getting all of the points in our Bergman fan? And the answer came from Sturmfels and Feichner, and it was a positive answer. It was yes. It was kind of technical if you're not familiar with flags of flats of matroids, but since you're attending this talk, you are familiar with them, so this is perfect. What this tells you is that your Bergman fan will always be decomposed into cones, 1 cone for each complete flag of flats. Perfect. So that means that whenever we want to compute things on Bergman fans, we can compute only things on the corresponding cones. And that's actually exactly what we're going to do. So let's go back. We want to compute degrees. What is the degree anyway? Here, in the algebraic geometry world, a degree of a curve, in this case a parabola, so we have kind of an intuition the degree is 2. And why? Because if we put a line through this curve, we'll get 2 points. Sounds like a definition to me. For any tropical variety, the degree will be, you take a hyperplane with the correct dimension, you count the number of intersection points, that's your degree. Now you have always to be a bit careful. You want to wiggle it a bit because you don't want your line to be tangent and count points with multiplicity 2 that you cannot count when you're using combinatorics. So this is what's called normally a stable intersection. You want to count the number of points in the stable intersection. In our world, tropical geometry world, hyperplanes will be Bergman fans of our uniform matroid. Perfect, we know this. Yeah, so let's go through an example. So we have a Bergman fan, now a different one, and we want to, this is a tropical variety, and we want to count the degree. So we intersect it with the corresponding, with the right dimension fan, which comes from a uniform matroid. In this case, graphical matroid K5 has rank 4, so dimension 3. We want to intersect it with a hyperplane of dimension 6, because the ambient space has dimension 9. So we want to count the number of intersection points between this fan, the Bergman fan of the uniform matroid, and this fan. And we do sort of a wiggle. This is this displacement. If the displacement means something to you, that's probably this. You're displacing one of the fans a bit by some generic vector. And then you count how many points are in the intersection. It turns out there's only one point. This motivates what was actually in the title of the talk, which no one has complained yet, which is great, that I was talking about linear spaces. And Bergman fans are linear spaces in this sense. They are spaces of the degree 1. Perfect. The way that we know that this intersection is unique actually boils down to the greedy algorithm on matroids. If you want to optimize in one direction, you get a unique basis, and this unique basis will actually give you the unique flag. This is sort of the intuition. OK. I wanted to tell you about activities. So I made a slide for that. But actually, there was just enough time to mention activities. So I'll just mention them. If you have matroids, to each basis you can assign 2 numbers. You have first to order the elements of your basis. But then you can assign 2 numbers, internal activities and external activities. And it turns out that the number of bases with a fixed amount of internal activities and external activities will arise in the third polynomial. So this will be one chromatic invariant of your matroid. If you count these bases, you always get this number. Does not depend on the order. And these bases have a specific name. They are called NBC bases and beta NBC bases. And I guess the takeaway from this slide will be there are these numbers and there's these special bases. How do they arise in Bergman fans? Turns out that we can use them to compute the degrees. They will give us exactly the complete flags of flats. And this is actually the result that I wanted to show you today. I already told you this. There's the greedy algorithm. There's a unique basis that maximizes some sort of linear function. This tells you that this degree is 1. There's a unique intersection point. If you flip one of the flags, if you flip the matroid around, you get a different tropical space, which actually has degree, and counting the number of intersection points gives us the number of NBC bases. Yeah, so this again can also be done algorithmically. For each NBC basis, you can find the intersection point. This equality was already a result from a Deposito Han Katz, very celebrated paper. And what was done later by Agostini and many other people in 2021 was that if we find these other 2 tropical varieties and we take their intersection numbers, we get the number of beta NBC bases. And at this point, we thought, OK, maybe we can find a bijection between this number of intersection points and actually the bases. We can find a way of corresponding them one to another. With the extra advantage that the result from Agostini et al. Was for representable matroids. But you can get Bergman fans for any matroids. So this algorithm kind of extends this equality for non-representable matroids. And this is what we do. I have a very quick passing on how to do it. I guess the message that I want you to keep from this slide is that you just need to know 1 beta NBC basis, and we can compute you the intersection point. So let's go through it. The beta NBC basis will give you the zeros. This gives you the y. And kind of the compatibility and the sum condition, both of them together, gives us the 2 solutions. And this is all very algorithmic, and this gives us the bijection. Cool. I just want to highlight the literature. I mentioned Deposito Han Katz. there's this degree composition actually was done not by fan displacement, but by very nice other methods. The motivation for this result actually came from statistical results. This is something I want to emphasize. This came from computing the ML degree of fans on very real models that was helping other people in other areas. And this is where we present the result. Yeah, thank you very much.
Thank you. Do we have questions for Raoul?
So since you're getting NBC bases, I don't know the beta version, but do you have some relationship or explanation in terms of the Euler-Thurau algebra?
The question.
Can you repeat? Yeah, thank you.
Yeah, first I want to clarify the Solomon algebra.
The Euler-Solomon algebra for the Matroid.
So the question was, since we can count things with NBC bases, do we have some relation with the Solomon algebra? I'm not familiar with. Yeah.
Other question? No? Well, thank you.
I think Kyle has a
Also, we
question.
have one. Thank you.
Sorry, so could you say a little more about the NBC bases?
Sure. Yeah. So these are the number of the bases. It's a number. It counts the number of bases that have a specific count on the activities. I told you there's these numbers, the number of internal activities and the number of external activities. If you actually find the bases with 0 internal activities and 1 external activity, this is a beta NBC basis. And these are the bases that we use to find these intersection points. They depend on the order that you fix. So if you change the order, you get a different beta NBC basis. So you may think, oh, this actually changes the algorithm. But actually, the algorithm depends on the vector W that we started with, this generic W here. This generic W actually already imposes an order on the ground set. So yeah, with this, we have a notion of beta NBC bases, and we can proceed with the algorithm. There's another question?
Yeah, could you say something if the weight is not generic?
If the weight, yes, sorry, I should repeat. What happens if W is not generic? I don't think I can tell you much other than, I don't think I can tell you much. That's, yeah. What we did was for this specific W, which sounded generic enough to us, and of course it works for W close enough. Now, if you pick some W that is like in a specific hyperplane where we don't like, I don't know what happens. But that's actually a very interesting question. What happens? I don't know.
Yes.
Thank you, Robert, for this nice talk. When you were talking about the minus fan, you were saying like flip the matrix. Can you like explain that a little bit more? How should I be thinking? I guess my question is, how should I be thinking of the negative fan of the matrix?
Okay, the question was, how should we be thinking about the negative of the Berman fan? So I presented you without defining. That's my fault. A point in the negative Berman fan will be just plugging minus everywhere. And of course, this corresponds to a negative, to a maximum attained twice condition on the cycles. That's how I usually think about this negative. Chris also mentioned in passing that this is the Cremona map. I don't know a lot about the Cremona map, so maybe this tells something to some of you.
I think we have time for one more question. I saw. Yep.
So the NBC bases give you the Mobius function for the lattice of flats. Did the beta NBC bases give you is there an easy function on the lattice of flats that gives you the beta NBC bases?
So the question was, the NBC bases give you the Mobius function on the lattice of flats. What does the beta NBC basis count? I can tell you, so there's in this room plenty of people that can answer this much better than I can. I can tell you that if your matrix comes from hyperplane arrangements, beta NBC basis, the number, is the number of bounded regions by these hyperplane arrangements. Yeah.
Thank you, Raoul.